Till now we learned about SN2, SN1 and E2 mechanisms. Now we are going to look at the last one, which is E1 mechanism. So again, this is an elimination reaction, meaning that we still have abstraction of beta proton, formation of double bond, and loss of leaving group. So in E2 mechanism, all of these happened at the same time. However, in E1 mechanism, these are happening in two steps. So it's a stepwise process. Now, the first step in the E1 mechanism is loss of leaving group. And after loss of leaving group, we are going to form a carbocation. So this step is exact similar as SN1 mechanism. So we are forming a carbocation, and whenever we are forming a carbocation, we need to consider the chance of rearrangement. Now, similar to SN1, this step is a rate determining step. Therefore, the rate law for E1 mechanism is only dependent on the concentration of substrate. Therefore, E1 mechanism is unimolecular. And it is also clear in its name. So, elimination, unimolecular mechanism. Let's look at the example of E1 mechanism. So, we are going to use the alkyl halide as a substrate again. So the first step is loss of leaving group, similar to SN1 mechanism. So leaving group leaves to form the carbocation. Now, if the carbocation can do rearrangement to form a more stable carbocation, it will definitely do it. However, here, this carbocation, which is a tertiary carbocation, is pretty stable and it cannot do rearrangement. So, in the next step, we are going to have a weak base. So, with E1, we are using a weak base, such as ethanol. So, the base will take the beta proton and forms a double bond. So the product is still an alkene. Similar to SN1 and E2 mechanism, E1 also prefers a tertiary substrate. So the tertiary alkyl halide is more reactive. Basically, it is the most reactive substrate. Then we have the secondary, primary, and methyl is almost unreactive. And the reason behind that is because we are forming this intermediate, which is a carbocation, and the more substituted the carbocation, the more stable it would be. So the E1 mechanism is faster with the tertiary carbocation. Now let's look at the regioselectivity in E1 mechanism. So because we are forming a carbocation, we always get the Zaitsev product because the carbocation rearranged to form the most stable one. So we don't get the chance to think about the kind of base that we are using. So we always get the Zaitsev product in E1 mechanism. So if you look at this example, this is the alcohol. And we are going to add concentrated sulfuric acid as a reagent here. And we are going to form both of these products. So one of them is Zaitsev. This is the Zaitsev product. And we are going to form that in 90%. So it's the major product, it's the dominant one, and this one is Hoffman. So we get 10% of these. Before I talk about the mechanism for this reaction, let's talk about the concentrated sulfuric acid that we are using. So concentrated sulfuric acid is actually the mixture of sulfuric acid and some percentage of water. So when we say concentrated sulfuric acid, that doesn't mean we have 100% acid, because it's going to be very dangerous. So the acid has a little bit of water in it. And then sulfuric acid will react with the water, and through acid and base reaction, it is going to form H3O plus and 4 minus. So the acid that is forming when we have concentrated sulfuric acid is hydronium ion. Okay. Now let's look at the mechanism for this reaction. So previously we talked about that this substrate is an alcohol, and one of the ways to convert the OH to the good living group is use of the acidic condition, and the acid that we are using here is hydronium ion. So OH will attack the acid to take the proton through acid and base reaction. So we are going to form this intermediate. Oxygen with 3 bonds is positively charged, and here we have water that leaves. And so now we converted the OH to the good living group, which is water. So the first step in E1 mechanism is loss of living group. So water leaves to form the carbocation. Now, can this carbocation do rearrangement to form a more stable carbocation? No. So next step, again another molecule of water acts as a base. So we are gonna have the beta proton here. So carbocation is completely planar, therefore it's easy for water to approach the beta proton to form the more stable carbocation, the more stable product. So water attacks the proton and forms a double bond. So this is going to be our major Zaitsev product. Now the stereoselectivity for E1 mechanism is similar to E2, so whenever is possible, it is going to form the more stable product, which is the transalkene. So when we have symmetrical you can obtain cis and trans product, and trans is always favored, is the major product. Let's look at this example. Again with concentrated sulfuric acid and heat. This triangle means heat, so we are going to form trans and cis product. So this alcohol is symmetrical, so we have 2 beta positions and they are identical to one another, so we are going to form trans and cis isomer. Trans is the major product and this is minor. Now if you are interested for the percentage, we are going to get 75% of this and 25% of that one. So this table is the summary of what we talked about substitution and elimination reactions. So it's a great comparison between all four mechanisms. You can read through it and hopefully it can help you to understand the concept better. To put everything together, there is a nice chart in your textbook that you can use to determine whether the substitution or the elimination can happen. And also it can be helpful to determine the product for a specific reaction. So to use this chart, I encourage you to do lots of practice problems. Now, how can you use this chart? So in the top part, right here, we have a list of reagents. So we can have strong base and weak nucleophile. Some molecules are just a strong base and they are not good nucleophile, such as sodium hydride, DBN and DBU that we talked about. Some molecules are both a strong base and a strong nucleophiles. Some of them are weak base, but they are strong nucleophile. And we can have some molecules that are both weak base and weak nucleophiles. Now, if you have a strong base and weak nucleophile, such as sodium hydride, DBN, and DBU, it doesn't matter whether you have primary, secondary, or tertiary substrate. With these type of reagents, always E2 mechanism can happen. And when E2 mechanism happens, you need to think about regiochemistry, stereochemistry, and all of those stuff that we talked about. Now, if you have weak base and weak nucleophile, such as water, methanol, and ethanol, with primary and secondary, no reaction will occur. And with tertiary, we are going to get the mixture of E1 and SN1 product. Now, some reagents are weak base, but they are strong nucleophile, such as all the halogens, and the reagents that contain the sulfur. So with these type of reagents, with primary and secondary substrate, we are going to have SN2 mechanism. So you need to think about inversion of configuration. And with tertiary substrate, we are going to have SN1 mechanism. So you need to think about formation of racemic mixture. Now with a strong base and a strong nucleophile, such as hydroxide, methoxide, and ethoxide, with tertiary substrate, E2 can only happen. With secondary substrate, we are going to get both E2 and SN2 product. However, E2 is the major product. And with primary substrate, we are going to get SN2 as a major product and E2 is going to be the minor product. So this is how you can read through this chart and basically practice with that. Hopefully it can be very useful while determining the products for specific reactions for you. Another point that I would like to mention is about the substrate. So in this chapter we learned that alkyl halides can act as good substrates for elimination and substitution reactions. We also saw some examples for alcohols. So alcohol can also act as good substrate. However, OH is not a good leaving group, and we learned two different ways to convert OH to the good leaving group. One of them was use of acidic condition, where we convert OH to water, and water is a good leaving group that can basically leaves the molecule, so it can be a good substrate for these type of reactions. And the second way was use of tosyl chloride and pyridine, where we converted OH to tosylate, and tosylate is a decent leaving group. So I would like again to emphasize that when we are talking about primary, secondary, and tertiary, it is not only about alkyl halides. It can include alcohols as well. Now, after examining the reagent and the substrate and figuring out which mechanism is happening, we need to look at regioselectivity, stereoselectivity, and stereospecificity in the products. So let's review all of these one more time together. So in SN2 mechanism, if you remember, the nucleophile attacks the alpha position and the leaving group leaves. The mechanism is conserved and the product would have inversion of configuration. Now with SN1 mechanism, so the leaving group leaves the molecule, so we are forming a carbocation first. Therefore, we need to consider the possibility of the rearrangement. Now, the product for SN1 mechanism is a racemic mixture. So we are going to have inversion and retention of configuration. Now, here is the point that we didn't discuss before. So it is reported that sometimes the inversion of configuration is preferred over the retention of configuration, but we are going to skip that part for now. Just know that we are going to make racemic mixture, inversion and retention of configuration. Now with E2 mechanism, so if you remember with the small bases, always Zaitsev product is favored. So Zaitsev product is generally favored with the small bases. Now with bulky bases, Hoffman product is always favored when we have a bulky bases. Now this process is stereoselective, meaning that trans disubstituted alkene is always favored over the cis. The E2 mechanism is also stereospecific, meaning that if you have one beta proton, the stereoisomeric alkene that is resulting from anti-preplanar elimination is always favored. So the abstraction should happen over the anti-coplanar conformation. Now for E1 mechanism, so because we are forming a carbocation in E1 mechanism, Zaitsev product is always favored. This process is also stereoselective, meaning that trans disubstituted alkene is always favored over the cis disubstituted alkene. So this is the summary of what we discussed. So I strongly encourage you, do lots of practice problems, use this slide, the previous slide, to figure out the product and the stereochemistry of the product. Now let's see how can we use this chart to figure out the product for a specific reaction. So the first step is to look at the reagent. The reagent that we have here is sodium hydrosulfate, so it's a sulfur containing molecule, and in the chart the sulfur containing molecules are right here. So they are weak bases and strong nucleophiles. Now if you look at this table, with weak bases and strong nucleophiles, either SN2 or SN1 can happen. So from the reagent, I figured that it's a weak base and a strong nucleophile. Therefore, either SN1 or SN2 can happen. Now, to figure out which one is happening, I need to look at the substrate. So, this molecule right here, OTS, is the tosylate. So, if you remember, tosylate was a very good leaving group. So, this is going to be my alpha carbon. And if you look at the alpha carbon, this is a secondary substrate. So the substrate is secondary. Again, you need to look at the chart. We are in this column. Now with secondary substrate, always SN2 happens. So the product is a substitution product. So let's draw the product. So SH is the nucleophile, attacks the alpha carbon, and leaving group leaves. So all of these are happening at the same time during SN2 mechanism. So we are gonna substitute the tosylate with SH. So the sodium is a counter ion, so basically we can ignore it. and or basically I can say the counter ion stays with the tosylate that left the molecule. So the counter ion stays with the leaving group. Now, do I need to show a stereochemistry here? Yes, because this carbon is connected to 4 different groups, so it's a chirality center. Now, if you remember from SN2 mechanism, we had inversion of configuration. So whatever was the configuration in the starting material, we need to flip that in the product. So the SH will be in dash. Actually, let's redo it. Okay. So SH should be in dash. So this is the major product for this reaction. Now let's look at this example. So again, the first step is looking at the reagent, which is sodium ethoxide. So ET is ethoxide, and if you look at the table, ethoxide is a strong base and a strong nucleophile. So from ethoxide, I know that is the strong base and a strong nucleophile. Now with the strong base and strong nucleophile, either E2 or SN2 can happen with primary and secondary substrate, and with tertiary substrate we only have E2 product. Now let's look at the substrate. So the bromine is my leaving group and the substrate is secondary. So from the substrate I figured that both E2 and SN2 can happen. However, E2 is favored. So A2 is favored here. But we are still making the SN2 product. Now let's draw the substitution product, which is happening through SN2 mechanism. So to draw the substitution product, I'm gonna draw the molecule one more time here. So for the substitution, so through SN2 mechanism, ethoxide acts as a nucleophile, attack the alpha carbon, and leaving group leaves to form the product. And I'm gonna make the chirality center, so I need to show inversion of configuration as well. So this is the SN2 product. Now to show the elimination product, and elimination is happening through E2 in this molecule. Therefore, so first we need to figure out the beta protons and find them. So how many beta position we have in this molecule? 2 beta position. This is 1 and this is 2. So therefore, if I remove the beta proton from this beta carbon, I'm gonna get this product. Okay. Now if I remove the beta proton from this carbon, So ethoxide acts as a base here. So if I remove this beta proton, I'm gonna form a bond here and leaving group leaves. So I'm gonna get both of these products. The top one is the less substituted alkene, so it's a Hoffman product, and the bottom one is the Zaitsev product. So Zaitsev product is the major product. Hoffman is minor, and I also, in this table, we also know that SN2 product is also minor. So there are 3 products for this reaction. Let's redraw all of them here one more time. This product is the SN2 substitution product, which is minor product. Then we are gonna form Hoffman product, which is also minor, and Zaitsev product, which is a major product. So Zaitsev is more substituted alkene. So this is how we can use these charts to figure out the product for a specific reaction. Let's talk about synthesis a little bit. So I believe synthesis is a very fun part in organic chemistry because you can become creative as much as you can while doing the synthesis problems. So basically in synthesis process, we are taking a less valuable, a cheap substrate and convert it to the more complex and useful product with different reagents. So the goal of synthesis is not to recreate your starting material. We are going to use all the reactions that we learned till now, E1, E2, SN1, SN2, and the reagents that we learned about in this class to form new molecules. There are a few types of synthesis problems that you can see in this class. So we are going to talk about one of them right now, and after we complete chapter 8 and 9, we are going to work on synthesis more. So in the first type, which is the sequential synthetic steps, we are going to take the substrate and convert it to the product. Then this product will act as a substrate for the next step to form the more valuable product, which is our final desired product. So we need to figure out what type of reagents we need to use to do each transformation for these 2 steps. Now for the first step, to figure out the answer, we need to compare the starting material and the product. So the starting material is an alcohol. I have OH group here. And the product, the OH group, is converted to tosylate group. So if you remember from SN2 mechanism, we could use tosyl chloride and pyridine to convert the alcohol to the tosylate. Basically, we are converting alcohol to a better leaving group. Now in the second step, this structure acts as a substrate to form the alkene product. So I know tosylate is a good leaving group, therefore this is my alpha carbon and I have 2 beta positions. So elimination happened here because I made an alkene. Now if elimination happens over this carbon, because I have 1 beta proton here, I would make this product. Okay, but if elimination happens over this carbon, I'm gonna make this product. Now this product is the more substituted product, so it's a Zaitsev product. However, this one is a Hoffman product because it is less substituted. Now, if you remember from E2 mechanism, to do basically to do elimination and form the Hoffman product, we need to use a bulky base. So for this transformation, for example, you can use tertiary butoxide, such as sodium tertiary butoxide, as a reagent to complete this transformation.